Hello everyone and welcome to our webinar. Today this is a special webinar. We are directly here from the EMC chamber. Here we are in the absorber chamber, and next to us, we will next see it, there is also the shielding chamber. I'm very happy to do it here. Hopefully it will work. Also it's a little bit difficult also to with the camera and all the stuff. So if something's happening here behind the scenes, sorry for that, but hopefully everything will work out fine. So if you're interested in the chambers, if you want to test your application stuff, or then feel free. We have the, so it's possible to book the chambers here as well. Hopefully, you will see now the link, and then, just check it out. This just for information. Today with me is Christian Merz. He's design engineer for wireless power systems at Würth Elektronik, and as well Robert Schillinger. He's working as a field application engineer. And I think that's everything from my side. I'm happy to do it, and now I give it to the experts and we go right to them. So they are ready for us. So come with me. Hello, Robert and Christian.
Hello.
Hi, nice that you're here in our chamber in Munich in the High Tech Innovation Center. Sorry, I forgot about that. And I give the word, Christian, to you. Stage is yours. Enjoy.
Thanks a lot. Hello, also from my side. Today I want to give you a presentation about designing Qi2 wireless power systems as practical development and EMC optimization. So at first I want to show you how to build up a Qi2 transmitter from scratch, and then afterwards introducing our new Qi2 transmitter coil and tips for effective integration. Then I will give over to my colleague Robert, who will tell you about the measurement and reduction of conducted and radiated interference through systematic filter design. So what components do you need for a Qi2 system? At first you need, of course, an input power supply, for example, a USB Type-C or a DC adapter, which provides the energy for the entire system. Then you need an EMC filter. This could be, for example, a LC filter or ferrites, which ensures compliance with electromagnetic compatibility and filters out unwanted interference. This my colleague will tell you later how we did this. And then you need a buck boost converter, which converts the input voltage to the desired output voltage for the power electronics and regulate it depending on the load requirements. Also, an important part is a power full bridge inverter, which generates the high frequency AC signal for the transmission using MOSFETs and drivers. And then the most important component is the Qi2 transmitter coil, which uses a magnet structure according to the magnetic power profile, and then it inductively transmits energy to the receiver, typically with a magnet system for localization and efficiency enhancement. Then the core of the system is the wireless charging controller. So we use a charging controller from Infineon, so the WLC1115, and it controls the entire power delivery, control loops, signal demodulation, communications, and everything else what is important. Also, you need a trust or security IC. So for this, we just use the optical trust charge from Infineon, which is important for the authentication of the sender according to the Qi2 security requirements, and protects against tampering. And also for the ASK demodulator and signal processing is needed, which decodes the data communication from the receiver and processes feedback signals for the regulated power transfer. Then you need some sensors and protection, for example, current, voltage, or temperature sensors, and your foreign object detection, which monitors critical system parameters and protects against fault conditions. Also, you need a communication interface, for example, I2C or UART, which enables the external connection and control, especially for authentication and data transfer. The Qi2 standard defines the following function diagram. So you need first a reliable supply voltage supply, then you need an inverter and a resonant tank and also a primary coil. Also, you need a ASK modulator and a ASK demodulator and a FSK modulator, and also the authentication system. So how did we do this? So we used, as I already mentioned, Infineon WLC1115 IC, which has the following key components. At first you have a buck boost converter, then you need a full bridge inverter, a Q factor estimation circuit, an LC resonant tank, and the ASK demodulator. So let's have a look at these components. So at first, the buck boost converter. So you have your input voltage, which comes directly from the USB-C, which could be, for example, 5 volts or 9 volts, 15 or 20 volts. And at the output, you have you transfer this voltages to 3 volt up to 24 volts. And if you are in the buck mode, which means that the input voltage is higher than the output voltage, then the boost leg is deactivated by keeping Q3 always on and Q4 always off. In the boost mode, which means that the input voltage is lower than the output voltage, and the buck leg is deactivated by keeping Q1 always on and Q2 always off. Then you have an inverter. So in our case, we use a full bridge inverter with an LC resonant tank. So with resonant tank capacitors CR1 and CR2, and the switching MOSFETs Q1 and 2, and also the wireless power coil. So this I will go deeper lately. And you also need some snubber capacitance, CS1 and CS2, to reduce the MOSFET switching of the voltage. Also, you need a Q factor estimation circuit. So here you excitate the coil with a pulse at the input, and then you just see how much it degrades. So, for example, if you have no receiver, the degradation takes more time than if you have a receiver or foreign object detection, which you can see at the bottom. Then you can calculate the Q factor by which the voltage at the beginning and at the end, and at the time when the voltage occurs. Also, you have a switching resonant tank. That means, for example, if you have an iPhone 15, which uses the Qi2 MPP power profile, then it automatically switches with this 33 nanofarad on. And if you in the baseline power profile, for example, if you have an older smartphone which uses the Qi1 standard, then it automatically switches to the 400 nanofarad. So one also important part is the ASK demodulation circuit, which uses 3 different modulation types. So, for example, the current at the output of the buck boost converter, or the voltage from the coil itself by using a peak hold circuit, or using a phase demodulation. And then one of these 3 passes is used by switching MUX. And then the output, you have a low pass filter. Then as a result, you get a signal with a very small magnitude. For this, you have to amplify it. So we use an AC amplifier to increase the magnitude. And then also at the output, we use, again, a low pass filter to filter it again. And then we use a comparator so that we get out the 1 or 0 bit sequence. And then we give this information back to the IC, and then we have demodulated our receiver signal. The key component of the whole system is the Qi2 transmitter coil, as you can see here. So we have the coil itself, also a ferrite plate, and the special thing about it is the magnet ring. And also a permeable magnet shunt, which is just there for holding the magnet ring. Also, you have a top and a bottom enclosure. And then, as you can see here, so these are the components which are defined in this new Qi2 standard. So for this, I will hand over to my colleague Robert, who will tell you something about the filter design of the system.
Welcome in our EMC lab. As Christian said, I will show you the measurements for the Qi2 transmitter, and we start with the conducted emissions like the CISPA 16, and we use the borderlines of CISPA 32 for commercial environment. And we have here the AN for AC, and connect the DC supply or the inverter to DC together with the Qi2 transmitter to have a complete system. And this is what we will measure outside the chamber in the measurement tool. And now I will go outside and show you the results of the empty measurement without any load on the transmitter. Okay, I close the door to have more space. Now I will show you the results of the measurement, of the conducted measurement. And as you can see here, it's an empty measurement. We have relative less noise on the 150K up to 30 megahertz. And what you can also see is that we start the measurement at 9 kilohertz to 150 kilohertz. That's a new, or this will be new in the standard. It's coming up, and I will say, if you take measurements, measure this range from up to the future with your device to have more information for the future and see what happens below 150 kilohertz. That's a tip from my side. Then we will change to a load system. I will put a more or less empty mobile phone on top of the Qi2 transmitter, and we'll measure the conducted emissions again. And what happens? We see the noise floor comes a little bit up. We have here also a peak at the 360 kilohertz, like Christian said, the new system is running on. And we see also a lot of harmonics in the increasing frequency. It goes in a range which is not, or it's too close to the borderlines. And now we have the information. We must do anything on the 3 lines which are coming into the Qi2 transmitter. And in the chamber, I will show you shortly what I plan to do on the lines. Let us go back to the chamber. And if I see the graphs, I can see a harmonic on 360 kilohertz. That means I expect a differential mode noise on one or on all 3 lines. You have here, we have the ground line, we have the VCC line, and also a control line from USB side to get the high power system. And at first, I will start to insert in the VCC line a filter, a simple LC filter, trimmed to the 360 kilohertz of noise, which is coming from there. And I will do it not here, far away from the system. I will do it close to the system. But I think it's better to show it on the presentation. And for this, we will go back. Close the door. And for this, I have prepared some pictures. You can see here the LC filter. I take a 2.2 microhenry inductor and a 10 microfarad capacitor, which you can calculate by a formula at close to 36 kilohertz around, and we get at 360 kilohertz approximately 40 dBs of attenuation. That's the plan. Let's have a look on the measurement, what happens. not so much. We can see here again a high peak at 360 kilohertz. Also, the other harmonics are not really smaller than before. That means maybe the noise comes out on another line, for example, the CC line, because it's not a filtered line and it's have less impedance than the filtered VCC line, and for this the noise comes maybe out on this line. That's the next trial. I add the same LC filter on the CC line, like you can see here, a second one based on the ground. And hopefully now we have a success. Have a look on the measurement. Yes, we get better performance. We have here a gap and also the harmonics a little bit lower than before. That's a good way, but it's not perfectly. And before we go to the radiated chamber, where we can see what happens above 30 megahertz, I can say to you, yes, it's good, but for radiated, it's not enough. And for this, I add an additional component in the system. I manipulate also the ground line. And we add here also a 2.2 microhenry inductor in line close to the transmitter device. And again, we have a look on the conducted measurement and get a big success. What also helps us in the second chamber. Now I will go to the absorber chamber and show you what we are do there. What is the building of the measurement or the measured equipment. We have here the table in the height of the middle of the antenna, and we will put here the Qi2 device with a supply from the left side, and also with the load is a mobile phone, and we measure in horizontal and also in vertical direction. And that is what I show you again on the presentation. We have there some pictures. Okay, let us close to measure. Yeah, back at presentation. Here we have a picture of the setup. We are measure again according to CISPA 16, also the limits for CISPA 32 for a far field, and we only measure the radiated emissions. We measure up to 1 gigahertz. That would be enough. But we have also a look on the range up to 6 gigahertz. You can see here, we have here a little bit trouble with 2.45 gigahertz. That's the mobile phone and the Wi-Fi module inside the mobile phone, because it's trying to communicate with a Wi-Fi system. And for this we see it, but it's not included in the test. It's not a reason for a fail. What we also see, if we have the complete filter on the lines, the 2 LC and the L in the ground line, we have in vertical direction of the antenna, a big gap to the border line or to the limit line, and close the same at the horizontal direction, a little bit more here in this frequency range, but at the end, we pass the whole radiated test. What I can show you now is what would happen if you don't filter the system. Then you get these results. For vertical antenna, you are close or too close to the limit. And if you measure in horizontal direction, you're above the limits. And this is a completely clear fail. you can't reach without any filtering to get an CE mark for your device. Yeah, thank you for your attention. Now we go back to the questions.
Yeah, hello together. My name is Silas Zorn and I will moderate the Q&A session. Yeah, thank you Robert and Christian for your interesting presentation. Now we will come to your questions. Before we start with the Q&A session, I will share the handout from the webinar today. And now everyone can download it. Okay, Robert and Christian, are you ready for the questions?
Yes. Yes.
Perfect. Then, first question. Is this one. Which typical challenges occur most often when developing a QA transmitter, especially regarding coil integration, layout, and EMC performance?
Yeah, that is a very good question. So regarding the coil integration, you do not have to you do not have any problems because it's a standard design. It means you just can integrate it without worrying about it because everything is defined in the standard and it's made to be used for this Qi2 transmitter. Regarding the EMC performance, as my colleague Robert already told you, you have to make sure that all the EMC regulatories are passing. So that's why you need some kind of filtering, as my colleague already told.
Okay, thank you. Then next question. How can one ensure that the LC resonant tank remains within the desired frequency range despite component tolerances and coil variation?
Yeah, so there are some component tolerances, that's correct, and also some coil variation. For example, the inductance is varying a little bit. But here it's the same answer like before. So because it's standardized, it's already taken into account that there's some variation. Also, the Qi2 system allows a little bit of a frequency range. So that's also not a problem at all.
Thank you. Then next question. I noticed that all the wireless charging ICs from Infineon are obsolete. Is there any particular reason for this?
Yeah, so that is a big problem. So we started to make the design in the last months, and then some weeks ago, very surprisingly, Infineon discontinued all wireless charging ICs, and I also had a meeting with them, and they told me they step out of the wireless power business completely, and also discontinued all ICs and will leave this business. But I didn't get any reason for this, so you just have to ask directly at Infineon.
Thank you. Then next question. In the EMC tests, we see that not only the supply line, but also the CC and the GND lines require filtering. Which inductors show early on that these coupling paths will become relevant?
As you know, every electronics which is able to convert voltages from up to down or from down to up, and also the wireless power system is a kind of transformer and voltage transformer, and for this you have a switching system, and every switching system creates noise. And if you have a cabling to the device and you have noise on the device, then you have a path outside this device. And in this case, we can see we have the noise on the VCC line, but we also notice that it brings not so much to filter it, and for this I take the second line, the CC line also, and get a filter there, and then it works. And why it works on CC line and not on the other line? That's the reason, because the noise is coupling everywhere. And if I have in one line a high impedance, then the noise see a block and search for a lower impedance way. And in this case, the CC line was this way, and we see it in the measurement after the listen. For this, you must block every line, and at the end, we also take an inductance into the ground line, and we get the best result. Maybe it would be also possible to change to a common mode choke. It's also could be a good question. Maybe the question is coming in the next parts or questions. But I don't try a common mode choke. I only try the differential mode filter, the LC filter thing, and the result. And for this, I do no more, or I take no more energy in searching a good solution, because if I below minimum of 10 dB below the limit line, for me it's okay. If you like the absolute best solution, then you can also try and common mode choke for sure. But in this case, the LC filtering was completely enough.
Thank you. Then, next question. Do you have somewhere the layout for the design to download?
Well, originally we planned that we provide all the layouts and schematics and everything to our customers end of this year. But unfortunately, because it's surprisingly it's obsolete, so we will not provide it anymore to our customers.
Then next questions. Would a shielded cable with metal braiding not help for the radiated and conducted immunity?
Yeah, in principle, more in the radiated. You have a chance to work with shielding, with shielded cables. Yes, it brings a advantage, but not for the conducted, because the conducted, if you have a shield around the cable, but you measure you couple out the noise directly from the line, from the supply line, from the CC line, and in this case, a shield gives you no advantage. And you measure it also, the noise, because it's a conducted emission, and conducted emissions are measured on another way. For the radiated, yes, because you block the noise to go to the antenna, and then you break the path with the shielding. That's right. Yes, and for this, a shielded cable makes it better, but not perfect for every thing in EMC.
Thank you. Then next question. Is the CC line filter really needed? I would expect VCC and GND to be sufficient. CC lines to have communications that is attended with the filter.
Yeah, you see in the measurement, it's necessary to filter the CC line. The communication on the CC line is very low. It's a slow communication. For this, the filtering does have no effect on the communication. And yeah, it's the same problem I explained before on the other question, because you have the coupling on the CC line, and the CC line is important to have, because you must show or give the system the hint that it must support the system with more than 1.5 amps, in this case with 3 amps maximum, and this is only possible with pull down resistor connected to the CC line. For this you must connect it. The other way could be the common mode choke, as I try to explain. It could be help, but we don't try it. And for this, I can't say what kind of common mode choke brings the same effects.
Perfect. Then next question. This one. Do standard SMD filtering inductors tolerate the hot plug inrush current?
Yes. Inrush is a known problem if you use ferrites. Maybe the attendee means this or goes in this direction. If you have a ferrite, it's a printed component with a printed structure inside, and these components have inrush or not so tolerable about inrush currents, but a classical filter inductor with a wire have no problems with inrush currents. It's too short, and the wire is too it's too strong to get in trouble with a peak pulse, a peak current pulse. But this is not a problem.
Thank you. Then next question. Question with 2 parts. First part is this one. What does it happen when putting the LC filter on PCB? Is there the risk the noise will jump over the filter and be not effective?
It's a point of design. That's correct, and it's a good question. If you put the filtering as close as possible to the output connector and try to give them a good ground connection and no possibility to couple via other copper planes or copper areas through the filter, then you have not a problem. It's only a design design stuff.
Thank you.
Okay.
Then I would say one question. This is the second question from the first one of the Infineon. Knowing about Infineon's decision to discontinue, would there be a different manufacturer that you recommended?
Yeah, so for this Qi2 standard, for example, there's from NXP some receiver chip, and for a microchip, for example. Also, if you're interested in the Qi1 design, so there are some receivers from Texas Instruments, for example. And for proprietary designs, I can recommend some ICs from Analog Devices. If anybody's interested, I can also send a list of active wireless power ICs and development kits.
Thank you. Okay. Perfect. Okay, then I see one last question in the chat. This one, what twisting the cables reduce some of the noise?
Cable twisting, especially for VCC and ground, it's a good thing and a good part where you can reduce EMC noise, but for the special noise, the common mode noise, it's a good thing. For the differential, we see in this case, it would be not a solution. It's only for the conversion of the converted part of the noise in common mode. For this is a twisting okay, but it don't solve your problem with the differential mode noise. It's only possible with an LC filter, and in the low range of the frequency, we see at around 350, 360 kilohertz. It's also only possible with an LC filter with a power inductor inside, not with a ferrite. Ferrite is a completely wrong component for this noise, because a ferrite works in a very, very high frequency range of around 100 megahertz and not in the kilohertz range. That's an also important thing. Don't try a low frequency signal to filter with an ferrite. That's not a good idea.
Thank you. Okay, then I see no more questions left in the chat. If you have any questions, please write into the chat, and then Christian and Robert will answer them via email in the next days. So yeah, thank you, Robert and Christian, for your time, for the interesting presentation. Thank you for your attention. I hope you enjoyed it, and hopefully you see us on our next webinars from Würth Elektronik. Have a nice day, and bye-bye.
All right.
Yep. Bye.